Okay, everybody, welcome to PDE Math 365. So nice to see you again on All Hallows Eve. Yay. Just have a few things to talk about today. I want to put the final nail in the coffin on Fourier series, and I'll try to do this expediently. Friday's always a little bit looser in Math 365 PDE. So what we've been looking at series that look like this, that look like a naught over 2 plus an cosine nx plus bn sine nx. And these are the classical Fourier series. And this is scaled so that, or arranged so that x is from negative pi to pi, and f of x. Typically this is a Fourier series for function f, and function f is like a periodic function with period 2 pi on the real line. If it had different bounds here, then you have a slightly different setup. But this is the classical Fourier series, and we have these formulas for the Fourier coefficients, which I won't write down again. But modern mathematicians tend to do things slightly different. So we tend to use complex numbers instead of real numbers for our Fourier series. And I don't want to spend a huge amount of time on this, but I at least want to make you aware of the way that you can think about Fourier series using complex numbers instead of just real numbers. And it does have some tangible benefits. I'll show you exactly what I mean. So remember Euler's formula, e to the I theta equals cosine theta plus I sine theta. Have you ever seen the trick of using this to derive the double angle formulas for cosine and sine? I'll just do a little diversion since it's Halloween. You square the exponential function, and this is what? E to the I 2 theta? So this is why mathematicians like exponential functions more than working with these individually, right? Because you can do nice things like this. So this is cosine 2 theta plus I sine 2 theta. On the other hand, the square of this should be equal to that squared. And if you just square this and use that I squared is -1, then you'll get this nice result. So what do we get? Plus 2 times I times cosine theta sine theta, and then, plus I squared sine squared theta, so it's minus sine squared theta. And so if you write this in the form where like it's real part plus imaginary part, you get cosine squared theta minus sine squared theta plus I times 2 cosine theta times sine theta. So evidently, if two complex numbers are the same, then their real and imaginary parts must be the same. So this tells you automatically that, unless we did some algebra mistake, it tells you that cosine 2 theta is equal to cosine squared theta minus sine squared theta. And it tells you that sine 2 theta is equal to 2 cosine theta sine theta. So I think that's really, really kind of neat. Of course, you can prove these formulas other ways. You can prove them in ways that are completely elementary using the unit circle, but you can rediscover them, or you can remember them by using Euler's formula. And I only mention that because, I mean, y'all said you hadn't seen it, so there it is. But it also kind of reminds me of the relation of like what I'm about to show you also kind of reminds me of this, because it just turns out that working with these complex exponentials is kind of elegant and easy. And that's why mathematicians tend to use them for their Fourier series nowadays. So let me see. So now take the same function f, and now you could allow f to be complex valued if you want. And remember, real numbers are complex numbers too. So this completely subsumes, you know, this includes real valued functions as well. And I'm going to make a new Fourier series where I'm just going to take f and write the sum from, say, n goes from negative infinity to infinity. So indexed by the integers instead of the natural numbers. And I'm going to look at c times n times e to the I times n times x. And in your mind, you should recognize this as cosine theta plus I sine theta. And that's also a Fourier series if you like. I'm just going to drink a little water. Don't mind me. And why is this a Fourier series? Well, these functions, e to the I n x, constitute an orthogonal system. They're L2 orthogonal if n and m are different. So remember this business? It's, although I have to be a little bit more careful, because when you take the vector space V equals functions now from I mean, I could say C to C, but let's be civil. So functions from whose input is a real number and whose output is a complex number, and such that f is 2 pi periodic, and such that you want to say that the integral of f squared exists and is bounded, but in this case, f squared could be a complex number, and we want to frame this in terms of real numbers instead of complex numbers. So what you do is you take the modulus of f. So remember, so f of x is a complex number, it's a plus bi. Its modulus is the length of this, so a squared plus b squared, take the square root, and then square that. So instead of f squared, you take modulus of f squared. And ask that to be finite. So this is like space, this is like the L2 space of periodic L2 integrable functions from negative pi to pi. Then there's an inner product on this space. But now the inner product is no longer f times g. The inner product is f times g bar. So f times the conjugate. And why does that kind of make sense? Well, if you look at a times a bar, or sorry, let's call this complex number z equals a plus bi, and look at z times z bar, then this is a squared plus b squared. So that means that f, inner product with f, is this integral of the norm squared, or integral of the modulus squared. And you know, if you think of the complex number as like a point in R2, it's given by AB, then this is the length of AB squared. So like I won't get too deep into that, but that's just maybe to hope motivates you that you understand that this isn't like an arbitrary choice. It's a choice that kind of makes sense. And so when you use this definition, then this does become an inner product. It satisfies the three properties. And it induces a norm and a distance function in the same way. This is like the norm of f squared. And once you've got an inner product on a space, you can start talking about inner product of two functions. So now this is equal to e to the I nx multiplied by its conjugate, which is e to the I minus m times x, which is now e to the I x times n minus m. And you can show that this is just the same argument that, you know, break this up into sines and cosines or whatever, like, but you can show that this is zero as long as these two numbers are different.
Does it matter which one you take the conjugate of?
Well, you take the conjugate of the second one, and you get this relationship that f of g is now, like instead of symmetry, you get f of g is the conjugate of g inner product f. That's the one difference in the three properties. For you know, complex values, symmetry gets replaced with this.
I'm used to it being the first one, but I guess it doesn't matter all that much as long as you're consistent.
I've defined it with the second. Every mathematician I've ever seen has also done that, and
Is this another physics thing, or do you think maybe I just misunderstood my textbook?
the question is, might it be like a difference between physics and mathematics, where perhaps physicists put the bar on F instead of G? And I haven't read enough physics texts to know that, but I do know that this definition is the universal definition for mathematicians, and you're not going to find different authors writing it different ways. Okay. So it's an orthogonal system. It's a complete orthogonal system, and you can therefore, you know, take a function and express it Certainly, you can take an L2 function and express it in this manner, and instead of being associated to, f will be equal to that series in the mean square sense. And the same, the usual Fourier convergence theorems will apply. So if you've got a smooth function, then its series will converge pointwise to the function f. And so what are these coefficients given by? I'll just write down the formula. I mean, we could have figured it out from that, but just for expediency. It's 1 over 2 pi from minus pi to pi. F of x e to the minus I n x dx. So if you don't mind, and this will always be well defined if f is periodic and integrable. So if you don't mind using complex numbers, then you can make this replacement for a Fourier series. And these coefficients C sub n are going to be complex valued. Now there's a relationship between this Fourier series and that Fourier series. And I'll just write down what it is. Kind of telling you things today instead of taking like an overlong discursion into calculating it all, but I just hope you find this interesting. So C naught, so this goes from negative infinity to infinity. And the partial sums are understood to be, and goes from like a negative capital N all the way up to positive capital N. So that's what's understood to be the partial sum in this case. You're summing up the first, symmetrically, you're summing up the first capital N and the first, capital N with the negatives. And so you should say that this series converges if and only if this sequence of partial sums has a limit as capital N goes to infinity.
Where did 2 pi come from?
It came from this. If it's not orthonormal, if it's just orthogonal, yeah. So it tells you the constant. And so what's the relation between the Cn's and the A sub n? So C naught is just 1/2 times A naught. And I'm going to get, so let's take n bigger than 0. Let's take n to be positive. And then for positive n, Cn is 1/2 an minus I times B sub n. And the negative coefficient, C minus n, that's 1/2 an plus I times Bn. So I bet you can work that out with some algebra. So what this means is that using, I mean, I challenge you to do this, like taking this Fourier series and then making the literal substitutions. And then using Euler's formula, you'll see that this transforms into that. Like those are the substitutions that you need to make to, together with Euler's formula, to start with this and end up with that.
What is the, so there's constraint on it,
Well, it's not a constraint, I'm just writing different formulas. Yeah. See, you notice that, and I have to do that, right? Because these ends only go from 1 to infinity. But these ends go from negative infinity to infinity. So that's why I had to present it in that way. And you can also go the other way. You can also start with a Fourier series that's complex and then figure out the real version of it. So how can you do that? I want to write down this system. I mean, this initial constant is special, but like focusing on this, I want to write this down as a system of equations, like matrix times a vector. So like matrix times A sub n times B sub n, giving me formulas for Cn and C minus n. So for any particular n, you'll get like equations like this. And so what is this telling you? Isn't it like 1/2 and then minus I over 2 and then 1/2 I over 2? An minus bn, everything divided by 2, equals Cn, and then an plus bn over 2, an over plus bn over 2 equals C minus n. So just writing that as a matrix. And so you can invert those equations if you can invert this matrix. So if I call this matrix M, then I get this formula that for an and bn, just being the inverse of this matrix times Cn, C minus n. So I could imagine like a homework problem or something where like you're given some Fourier series, calculate the other version. So is this matrix invertible? You have to check that the determinant is not 0. So this is like 1/4 times I minus negative I times 1/4. So it's just like 1/4 I plus 1/4 I, right? So it's just 1/2 I. I know complex numbers, but still, the determinant is not 0, and therefore the formula for inverting a matrix, 1 over det m, will exist. The formula will be good. The inverse will be calculated for you in the usual way, and that tells you how to write out formulas for those. So anyway, kind of speeding through it, but this tells you a prescription for how to write formulas. A sub n equals whatever, and B sub n equals whatever, like in terms of the C sub n's, like you can use that matrix there to do it. Or you could just play with these two equations and use like the high school ad hoc method and also figure it out. But linear algebra kind of does it for you quickly. I didn't just want to tell this to you. There's one thing that I really want to show you. Because when we were looking at this paper, one thing I noticed in finding a closed form expression, we were able to take the Fourier partial sum and write it as like some fraction of sines over cosines, right? And that was a key. That was like a formula from which all the blessings flowed. And I think for a partial sum for like the ANs and BNs of the sines and cosines, I find it difficult to write down a closed form expression, although we lucked out in that particular case with square wave. But here I can have a hope of finding a closed form expression of this partial sum because this is geometric series, right? E to the I n x is equal to e to the ix to the nth power. So I have some hope of using the formula for sum of a geometric series to get like a closed form expression. I'll remind you the formula for sum of a geometric series. Yeah, that's right. So it's like 1 minus r to the n plus 1 all over 1 minus r. So this formula holds good no matter what. You can just get this with factoring a polynomial. Like if you take this side and multiply it by 1 minus r, you'll get a telescoping series that is equal to 1 minus r to the n plus 1. So that's fine. And whether or not this series converges when you take the limit just depends on whether or not this goes to 0. So you learn that absolute value of r, or more generally like modulus of r, has to be less than 1. And then as n goes to infinity, this series will converge to that. Although I guess I need this scalar a times that. Forget about that scalar. But we don't have exactly that, right? We have a double sum. So we need a different formula. And you can, this is, again, an algebra exercise, because you can sum the positive part with this formula. You can just re-index and sum the negative part with a similar formula, add them together, put it over a common denominator, and simplify. But I'll show you the end result of that, which is just to say, like if you go from negative n to n, you get something like, and I guess we're going to take a equals 1, so I'll kind of take that away. You get r to the minus n times 1 minus r to the 2n plus 1 over 1 minus r. So this is general formula for summing a geometric series, or for partial sum for the geometric series. And what I'll do for our particular use case, we're going to take r equals e to the ix. And so what I'll do in order to facilitate that is this general expression, I'll just multiply and divide by r to the minus 1/2. And so when I do that, I think I'm going to perform like this two multiplications straight across. So r to the n and then times r to the minus 1/2, giving me r to the minus n plus 1/2. And the first term and the second term is minus r to the n plus 1/2, everything over r to the minus 1/2 minus r to the 1/2. We'll check if I got the minus signs right. So minus n minus 1/2, and then there's a minus sign, and then multiplying this by minus n gives me just n plus 1, and then subtracting 1/2 gives me n plus 1/2. So it looks like that's correct. And so this is just r to the minus 1/2 over r to the minus 1/2. I'm multiplying by the number 1, of course. And so this gives me r to the minus 1/2 minus r to the 1 minus 1/2, which is r to the 1/2. So here's a formula, if you like, for sum of doubly indexed geometric series that holds good no matter what. No, I want to use this formula. I just want to make the substitution r equals e to the ix. And so when you do that, when you do r equals e to the ix and then make the substitution that well, do you have to use Euler's formula or not? Let me just write down the answer and we'll consider it. The answer is that you now get Sn is equal to this partial sum, and plug into that formula e to the ix in place of r, and you'll end up with sine of n plus 1/2 times x over sine of 1/2 times x. So I can explain that if you like. Let's look at the denominator first. So this is e to the ix to the minus 1/2. So isn't this just e to the minus ix over 2, and e to the ix to the 1/2 is e to the ix over 2. And so adding these together and using Euler's formula, e to the ix equals, cosine x over 2 plus I sine x over 2. Should give you this, perhaps times I, but then that'll cancel out with the numerator when you also do it there. And maybe I won't write out all the algebra, but is there any question about that? You're taking a difference between a number and its conjugate, and the cosine term is dropping out. You're left with I times the sine term, the i's cancel. And then you get that formula. This is called the Dirichlet kernel, so it gets relabeled as d sub n when you're using this particular formula. Oh, and sorry, so everything on the board is correct, but this Sn is obviously not that Sn, right? So these coefficients are not included in this calculation. This is just the sum of the first, this partial sum of these exponentials. Okay, so any question or comment on that? So then the next thing you might want to do is try to find. So maybe I shouldn't even call this S sub n because I've already written it here and defined it. So just erase that, and this sum of the first exponentials gives you that formula. That's what we've shown. So now what I actually want to do is find a formula for the Sn, for the partial sum of the Fourier series. That's what you're really interested in. And so this is that. And yeah, I'll actually show this. I'll actually show this. So this is like just replacing c sub n with what it's equal to. 1 over 2 pi minus pi f of x e to the minus I in x dx. So this is c sub n, and I'm multiplying by e to the minus I in x, and I'm adding it up. And what I want to do is pull out the constant. Since the integral is linear, I can take this number of terms. So, I can bring the summation inside the integral. Oh, we do something else. Yeah. So this is like. What do I want to use? Yeah, let's call these t. That's right. Because I do want to bring this inside the integral, and so I want to use a different dummy variable for integration. Yeah, thank you for the suggestion. Because x is fixed, right? You're plugging in x into this function, and then these constants c sub n are calculated with this integral that uses the dummy variable of integration. So it's not it wasn't wrong to write x here, but it's not helpful, especially if you want to move this constant inside the integral, which we do. So yeah, so let's do that. Let's bring out the 2 pi and take in the sum. And let's do f of t, and what is it? E to the what can we factor out here? N and I, and then I get x minus t dt. And now we're basically done. We're basically done, except with one step. So f of t, I cannot pull f of t out of the integral, but I will just use the distributive property of multiplication to put f of t outside of the sum. So this is now f of t times the sum. And then you're integrating that. But this you should recognize immediately, because this is now a sum of complex exponentials, and you've got a formula like e to the I n y is sine of this times y over sine of that times y. And so taking x minus t equals y, you'll see that this is now the Dirichlet kernel of x minus t dt. And I won't show this. You can do this calculation on your own if you like, but making a substitution, s equals x minus t, using periodicity of f, you can then show that you can do a little bit of calculus and show that this is the same thing as, dn of t times f x minus t dt. And I like writing this integral in this way because I can actually literally plug in that formula. And remember, this is the partial sum of the Fourier series. And this should remind you of something. If you're really paying attention, this will remind you of Duhamel's principle from earlier on in the course. This looks like 1 over 2 pi times the convolution of f with the Dirichlet kernel. You remember the definition of convolution. It's this. I mean, the way we defined it before, it was from negative infinity to infinity, but if you're willing to keep these finite bounds and use the same, and otherwise keep the definition of the same, then you can think of this as a convolution. So that's why we like complex Fourier series, because you've got this formula, specific formula, that then says the Fourier partial sums for any function, as long as it's integrable, are given by just integrating that Dirichlet kernel against f of x minus t. And why should you care about that? Because this is something that you actually have a chance of analyzing or computing a limit as n goes to infinity, like as you saw in the paper that we looked at. The first step was like we had to do something like that. And if you take a more advanced analysis class and you actually get yourself to a point where you're proving those convergence theorems, the first step to proving any of those convergence theorems is rewriting this in terms of that. And it's this integral that you're working with to do that kind of stuff. Okay. So I just wanted to quickly show that to you. It was very quick. It only took 50 minutes. Yeah, I hadn't decided whether or not to do it, but I said, you know what, we'll go ahead and make it so. Oh, excuse me for just 1 minute. Well, that's not the thing that made it fun, I hope. But anyway, we will now engage with maybe a little bit more. Well, like in just 6 minutes, in just the time it takes to sing "Rap God" by Eminem. I want to actually return to something we were looking at before. So we were doing some homework problems, and I actually want to kind of briefly overview a homework problem for you. I'll try to be sketchy and not show the things that are more reasonable and emphasize the things that are more difficult. So you should remember this from your homework. You had this equation, utt plus 2 u sub t equals uxx. And you had your domain was 0 from x to 1, and t bigger than 0. And you had some boundary conditions that u 0, t equals 0, u 1, t equals 0, u x 0 equals f of x, and u sub t x 0 equals 0. And you want to do this with separation of variables, so you hope that u is going to be a sum of like product solutions g sub n and y sub n using the books notation. So like the UNs are going to be product solutions of like g sub n of t and y sub n of x, right? And you're using separation of variables, which means that ultimately you want to sum them up n goes from 1 to infinity, and that'll be equal to u. Sturm-Liouville theorem, basically says that if you get a Sturm-Liouville problem when you do the separation, then you'll always be able to index it by n. You'll have this discrete set of eigenvalues. And so what you do is you plug in u sub n to the equation and do the classic separation of variables technique, and I think you're maybe quite familiar with that. And so you get y sub n double prime equals minus lambda times y. That's the separation constant. You get g double prime plus 2g prime plus lambda g equals 0. And what about the boundary conditions? So this is something that I think may give you some struggle, is thinking to yourself which boundary conditions go on the individual product solution and which boundary condition goes once you've summed everything up. And then you're plugging in t equals 0. And so my hint for that is, like, when you've got boundary conditions that are set equal to 0, that's naturally a good candidate to put on the product functions. In fact, our Sturm-Liouville theory starts with that. It says, like, your boundary conditions have to add up to 0. So this is my key, that I'm going to put these on the g sub n's or y sub n's, and this is my key that I'm going to, like, I have no hope of making the individual products equal to a function, but I can add them up and at this stage apply f of x. Okay, so this leads to yn of 0 equals 0 and yn of 1 equals 0. This is a Sturm-Liouville problem, and this leads to g prime. I guess I could have put in the n's. 0 equals 0. And just to discuss this one a little bit, when you take u sub t, what are you getting? Like, if you differentiate under the integral sign, you're getting g prime n times y sub n. And so when you look at u sub t x 0, then you're looking at g sub n prime of 0 times y sub n of x. And when you look at this, you have some choices to make. I mean, you're searching for a solution, and so what choice are you going to make? Are you going to assume that all theyn's are the 0 function? No, you definitely don't want to do that. You're actually looking for non-zero solutions, right? And so what's your other option? Makes sense to assume that at the point t equals 0, these derivatives are equal to 0. So that's how I'm getting that boundary value there. For the y sub n's, I won't discuss this because this is like something we've seen quite a bit. But enforcing those boundary conditions, you find out that root lambda is equal to n times pi, and your y sub n is going to be a constant times sine of root lambda times x. So n pi x. So there's your first product solution. So this one is more interesting, right? So this one is second order constant coefficient ODE with this one condition, and it has characteristic polynomial r squared plus 2r plus lambda, but lambda is equal to n squared pi squared is equal to 0, and so that gives you, using quadratic formula, that r is equal to minus 1 plus or minus root 1 minus n squared pi squared. And so you should think of this as, like, there's two cases. So either n can be 0 or n is bigger than 0. If n is equal to 0, then your two roots are just like r equals 0 and r equals minus 2. And so then, like, working in this setup, so with r equals minus 2, you're getting something like g0 equals e to the minus 2t, which doesn't satisfy this condition. So you cross it out. With r equals 0, you get g0 equals constant, which does satisfy this condition. Okay, so now you've handled n equals 0, so you rewrite this as minus 1 plus or minus I times square root of n squared pi squared minus 1. Right, so now this number is positive, and you just factored out the root -1. And I would like to write alpha for square root n squared pi squared minus 1. And so now I'm getting minus 1 plus or minus I alpha. And so it's giving me two independent solutions for G sub n. It's giving me that G sub n should be a constant a times e to the minus t times e to the I alpha n. Well, I'll call this alpha n because it depends on n. Plus b times e to the minus t, multiplying this by t, plus sine alpha n times t, right? So you could use just e to the t times this, or e to the t times, times minus that, or you could put it back into sines and cosines and end up with e to the minus t times a cosine alpha n plus b sine alpha n times t. So this is the general solution, the general real valued solution of that problem. Skipped over a few things for this ODE review, but you can just put this into the complex exponential, use Euler's formula, take the real and imaginary part, then the linear combination of those two independent solutions gives you the general form. And using g prime of 0 equals 0 to this equation would then give you that minus a plus alpha n times b equals 0. So it gives you a relation to these coefficients. So a is equal to alpha n times b. So you get this like alpha n here times b times cosine alpha n t. So this is your general form of the solution that satisfies the initial condition. And I'll remove this constant b. You don't need to put in the constants until you multiply them together and add them up for the series. And so this now tells you that uxt is equal to the sum of the products of the solutions. And so now I'll put in the constant. So like whatever you want to call it, like C sub n or A sub n or whatever. And I guess you're starting with G0 equals well, I guess you've got, I'll add on the 0 term second. N goes from 1 to infinity of sine n pi x times this G sub n times a constant, call it C sub n. And then you've got this n equals 0 term, which is going to be constant times sine 0 pi x, which is 0. So it vanishes and it's not there. So this is your uxt. And you've got f of x equals ux. 0 is the sum Cn. And so what happens? Cn times sine n pi x. And when t is equal to 0, e to the minus t is 1. Sine alpha n times 0 is equal to 0, whereas cosine alpha n 0 equals 1. So you actually get this alpha n term there. And if you just take the inner product, like L2 inner product of f of x with sine n pi x, that's what you get on the left-hand side. On the right-hand side, this will be 0 unless the two coefficients are the same, and then you're left with c sub n, and you have to divide by not just sine n pi x, sine n pi x, but also by alpha n. So you get this extra factor of alpha n there. And so this L2 inner product, I think we know by now it's always pi over 2.
Well, on the bounds.
Or I guess it's always 1/2. Yeah, sorry about that. This is always 1/2. The bounds are 0 to 1. Yeah. So this gives us that c sub n is equal to this integral from 0 to 1, f of x sine n pi x times 1/2 and times 1 over the square root of n squared pi squared minus 1. So that solves the problem. Here's uxt, and here's a formula for the coefficients. Yeah, 1 over, so it's 2. Yeah, thank you. So this integral is 1/2. So 1 over that is 2. So that's the solution to, and that modeled a vibrating string underwater. And yeah, so I went into office hour time to do this. I apologize for that. But I thought you might be interested in seeing the full solution of the homework problem. I skipped a couple steps figuring out this, which I think you're familiar with. And I glossed over the concept of taking a complex solution and finding the two real solutions from ODE, but hopefully we're also kind of familiar with that too. And so I guess I'll give you one more weekend with no homework, but starting on Monday, I think I'll give you a problem like this to do for Wednesday, and starting on Monday, we'll broach into some new topics, and then we'll start with daily homework again after that. So thank you, everybody. Happy Halloween. Midterm 2 is a week from today. Yeah. Yeah. And this is not a surprise to you at all because the schedule has been there since the beginning of the semester. And I also gave you a note about it 2 weeks ago. Okay.